Hey, so today we're going to be talking about the potato and its role in polynomials. Yes, there is a connection actually. All right, but before we get to that connection, I want to play a little game for bell work. I'm going to ask you, is this a polynomial? Okay, so here's the first one. Y equals 3x squared plus 4x minus 5. Is this a polynomial? 5, 4, 3, 2, 1. Why, yes, this is a polynomial. Good job. How about this one? Y equals 2x minus or plus 1. Is this a polynomial? 5, 4, 3, 2, 1. Yes, this is 2. How about this one? Is this a polynomial? Y equals negative 4x to the 7th plus 12x to the 4th minus 3x squared plus 7x plus 1. Is this a polynomial? Sure is. Didn't even need a countdown for that. But how about this one? Is this a polynomial? 5, 4, 3, 2, 1. Yes, yes it is. Huh? Mr. Gukla, I don't know any Greek, but I know enough Greek to know that poly means many. And so this is supposed to be many terms. You've got just one term there. Yeah, well, so that's sort of the problem with imprecise translation. Really, what we know is that a polynomial is a function that can be written in the form, and now I'm about to write something down. Don't be scared about it until after I explain it, okay? Okay, so here's our polynomial. Y equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1. And so on, dropping the power down by 1 each time until we get to a sub 2 x squared plus a sub 1 x plus a sub 0. So if we can write the polynomial in this form, if we can write the function in this form, then the function is in fact a polynomial. Now, these things, these represent the coefficients in front of x. This isn't any math. This is part of its name. Hi, I'm the number in front of the term that is x to the nth. Hi, I'm the number in front of the term that's x squared. Hi, a sub 1. I'm the coefficient in front of the term that is x to the first. And this is times x to the 0. We know x to the 0 is 1, so I'm just that number that might be there at the end. So these are just numbers. And so when I see something like y equals 3x squared plus 4x minus 5, I think a sub 2 is 3, and a sub 1 is 4, and a sub o is 5. And so I think I've written in that form. But wait a second, what happened to all these other terms? Well, what made them go away is I had a 0 here, and a 0 here, and a 0 in all those other terms until I got to that one. And so this is all that was left. So what about this one? 2x plus 1. Well, I put a 0 here, and a 0 here, and all of the zeros in front of these other terms, and then a sub 2 is 0. But a sub 1 is 2, and a sub o is 1. So that fits the form. So then if I have something like y equals 4, I'm just putting in 0, 0, 0, 0, 0 for this one, 0 for this one, so that all that I have left over is a sub o, which is 4. This is a polynomial, okay? Now, another thing I notice is these powers are all whole numbers. There's no negatives, there's no decimals in these powers. So if you see something like y equals x to the 2/3 power, not a polynomial. If you see something like y equals x to the -1 power, not a polynomial. Okay? So no fractiony exponents, no negative exponents, no exponents that are negative and fractiony. Just won't do with polynomials. Can't write it in this form if they have rational exponents or negative exponents. Okay? So that's what we know about polynomials. Polynomials can be written in that form. We know some other things too that I'm pretty sure you've picked up over time. So here I want leading coefficient t, positive, leading coefficient negative, and here we have even degree, and here we have odd degree. Remember, the degree is the highest power in the polynomial. So if I have something like y equals 2x to the 3rd plus 5x plus 1. Well, here's x to the 3rd, here's x to the 1, here's x to the 0. This is the highest power, and so I would say this is an odd degree polynomial. But if I had a 4 over here, then 4 is bigger than 3, which is bigger than x to the 0, so 4 would be an even degree polynomial. Okay? And we know something about the end behavior of polynomials, like an even degree polynomial with a positive leading coefficient. There's one. What do you know about the shape of this graph? What do you know about its end behavior? As x heads to infinity, where's this function headed? Way up to infinity. What about as x heads to negative infinity? Where does this even degree polynomial with a positive leading coefficient go? Well, as x heads to negative infinity, this thing heads up too. Okay, now we don't know what's happening in the middle of the graph. You know, this is x squared, we know it bounces off the origin. But if I had x to the 4th minus 15x to the 3rd plus 7x squared minus 2x, yeah, I don't know. I imagine it's doing something like that. But I don't know, right? So all I can say is both ends go up. Now, if I have a negative in front of this, well, then we know both ends go down. What about an odd degree polynomial? We had one as our reference graph, y equals x to the 3rd. As x heads to infinity, where does y equals x to the 3rd go? And remember, that's a positive x to the 3rd, a positive leading coefficient. With a positive leading coefficient, we're heading up to infinity as x gets bigger and bigger. But what about as x heads to negative infinity? Well, we said it would go down forever. Now, if I had a negative leading coefficient, if I change this to a negative x to the 3rd, we know we're going to multiply all these y's by negative and all these y's by negative, and that's going to flip our graph. Okay? And knowing this end behavior stuff is actually going to be really, really helpful when it comes time for us to draw the graph of a polynomial. Okay? So we've got these 4 choices. Even degree, like y equals x squared, with a positive out in front, both ends go up. Even degree with a negative out front, that means both ends are going to go down. If we have an odd degree polynomial with a positive in the front, we go up as x heads towards infinity and down as x heads towards negative infinity. But if we've got a negative in front of that odd degree polynomial like this, that multiplies all these by -1, and so our graph is flipped. Okay? Okay, now, I do want you using end behavior notation. And for us, end behavior notation is going to be something that you won't see in the back of the textbook. So don't look back there. I'm certainly not going to take pictures of those pages because they say some wacky stuff for end behavior. And I know that a number of you are going to go on to calculus, either with me next year or when you go off to college. So let's see what end behavior notation I'm looking for. For example, if f of x equals x squared minus 5x plus 4. Okay, I see that it's an even degree polynomial with a positive leading coefficient. I know that both ends go up. But this is how I want you to describe that, okay? As x heads to infinity, f of x heads where? Well, as x's go this way, the function is heading towards positive infinity. And as x heads towards negative infinity, as the x values go this way, where's f of x going? Well, it's also going up. That's end behavior notation. End behavior notation. So if you're asked to describe the end behavior, this is what I need. Don't give me anything else. Again, don't give me anything else. Give me this. I need this. So please attend to what I need. Okay, what about f of x equals negative x squared plus 5x plus minus 4? Okay, so I reflect this graph. Now, because I have a negative in front of an even degree polynomial, I know this. And so how would I write that end behavior notation? I would say as x heads to infinity, where's f of x going? Well, f of x seems to be going down towards negative infinity. And as x heads towards negative infinity, as I go this way, what are the function values doing? What are the y values on this negative leading coefficient even degree polynomial doing? Well, as I go this way, y values seem to be headed towards negative infinity. And a hallmark of an even degree polynomial is both ends go in the same direction. Now, what if instead we had this function? What if instead we had g of x equals 2x to the third minus 5x plus 1? Can you describe the end behavior for this function? Remember, it's got a positive leading coefficient and an odd degree polynomial. What would its end behavior be? All right, like y equals x to the third. Okay, so write out the end behavior notation for me. Give it a try, pause the video, give it a try, come back when you're done, or if you're stuck and want to look and see. So I know as x heads to infinity, as we go this way, where's the function headed? Well, the function's headed up to infinity. And as x heads in the opposite direction, towards negative infinity, as I go this way, where's f of x going? F of x is going down, negative infinity. Odd degree polynomials going opposite directions. These are going opposite directions. Okay, last one. H of x equals negative 1/4 x to the fifth plus 2x squared minus 7. All right. I see an odd degree polynomial with a negative leading coefficient. Please write down the end behavior for that polynomial. Come back when you're done. Okay, so with an odd degree polynomial and a negative leading coefficient, we know that this side goes up and this side goes down. This side is up and this side is down. And how would I describe that? As x heads to infinity, f of x is headed where? Well, f of x is headed down as x goes this way, negative infinity. And as x heads towards negative infinity, As we go this direction, where's the function going? Well, the function's going up over here, so the function heads to infinity. Whenever you're asked for any behavior, I need you to give these n behaviors in our n behavior notation. Don't do it any other way, please. Okay, next, if we have a polynomial, like this one, this polynomial has this thing, and this thing, and this thing. Now, there's some interesting things about their names. So, let's say that this is A, B, and C. Well, I want to say x equals A, x equals B, x equals C are zeros of the polynomial. You might also know them as x-intercepts of the polynomial. Okay? We also know that if this is an x-intercept here, I could write this polynomial in factored form, x minus A, x minus B, x minus C. Because remember, the y value at each of these points is 0. So I'm saying 0 equals, and so what does this factor have to be if the answer is A? Okay, so I've got x minus A equals 0, and then I add A to both sides of this equation, and I get x equals A is an x-intercept. So what I'm trying to point out is, if I know that this is a 0, then I know that this is a factor. If I know that this is an x-intercept, then I know that this is a factor. Okay? So pay attention to the language. This is a 0, a root, an x-intercept. We've got lots of words we can use to describe this. 0, root, x-intercept. And here, we can turn those zeros, roots, or x-intercepts into factors of the polynomial. Speaking of factors of the polynomial, I want to tell you about this guy. He graduated college a while ago. His name is Thomas Harriot. And he actually went to Oxford College in England, very posh, prestigious school. Oxford and Harvard are often thought of in a similar vein, except that Oxford is a couple hundred years older than Harvard. So while he was at Oxford, he was getting a bachelor's degree. He studied some math, just like many of you will study some math. And when he got out of college, he was bumming around trying to figure out what to do with his life. He liked math, and he started studying navigation. And navigation was a new science at the time, and so it was sort of cutting edge, and that's what he decided to get involved with after college. And when he was 25, a gentleman came to him and said, "Hey, I hear you know navigation. Would you like to come on a trip with me?" And so Sir Walter Raleigh, who wasn't a sir yet, he was just Walter Raleigh. Sir Walter Raleigh had planned a trip to a place that white Europeans hadn't been to before. He wanted to go to the New World. Now, for all the Native Americans who were already living here, it wasn't the New World, it was just the world. And Walter Raleigh needed a navigator so that his ship wouldn't get lost at sea and he'd be able to find his way. So he asked Harriet, and Harriet said, "Sure, I'm up for adventure. I'm a recent college graduate with still trying to figure out what to do with my life at 25. very common story. And so in 1585, this story happens. They got on a boat with some other people and sailed to Virginia. Wasn't called Virginia yet. When they were there, Harriet found this thing called, well, it wasn't called a potato then. It's called a potato now. And he said, huh, look at this thing. And so Walter Raleigh brought it back as a gift to Queen Elizabeth, the Virgin Queen, and said, here, I bring you the potato from your new lands. And thus, we love French fries now. Thank you, Thomas Harriot. Well, it turns out that after his period of adventuring around, he went back to college and studied math and navigation and astronomy like crazy. And you know what he came up with? He came up with the fundamental theorem of algebra. I know, right? It's like we should have a parade for this guy, the fundamental theorem of algebra. Well, here's what he said. He said, if you have a polynomial of degree n, then that polynomial will have n zeros in the complex number system. And what he's saying there is, you can take any polynomial and break it up into factors that will have the same number of zeros as the degree of the polynomial. So if I see y equals x squared minus 1, I see y equals x squared, a degree of 2 tells me that this thing is going to have 2 zeros. And we know this has 2 zeros, one at negative 1, one at positive 1. Okay? So the degree tells me number of zeros. But he knows enough math to say, well, not all parabolas have x-intercepts. Some real x-intercepts. Some, like this one, have imaginary x-intercepts. Okay, so this one doesn't have any real x-intercepts, but it has, guess what? 2, because of this, imaginary x-intercepts. And we'll talk more about complex numbers and imaginary numbers later on in this unit. I just want to let you know something that's hugely obvious to you right now, that if you have a third degree polynomial, that means it has 3 zeros, or roots, or x-intercepts, and some may be real, and some may be imaginary. But the degree tells us the total number of zeros we can have for a polynomial. See a third degree polynomial, I'm expecting 3 zeros. They might be real, they might be imaginary. Okay? So that's going to help us, because if we know that the zeros are x equals a, x equals b, and x equals c, we also know that if we know how many zeros are, we can turn those into factors. And that's one of the reasons that factoring becomes this important thing, because if I know that the polynomial is, say, y equals negative x to the third plus 2x squared plus x minus 1, a third degree polynomial, I might have 3 real x-intercepts. I could have 1 real x-intercept and 2 imaginary ones, but those are my only 2 choices. So knowing this fundamental theorem of algebra, which admittedly feels kind of lame these days because, like, what's the big deal? Yeah, it was a big deal back in the early 1600s. This was groundbreaking, high technology stuff. And certainly, I would agree that it kind of was because, we're still teaching kids about finding zeros and how many zeros a polynomial would have. Almost 400 years, in fact, 400 years to the day, because he died in 1620. 400 years after his death, we're still using this piece of information. So I guess it really is a fundamental theorem of algebra. It's a really basic, important thing for us. Now, you're also likely to come into contact with this phrase, turning points. And turning points are these places. And so casually we might say maxes and mins. And you might be asked, how many turning points does your polynomial have? And the cool thing about turning points is that the maximum number of turning points is n minus 1, where n equals the degree of the polynomial. So here, because this end is going down and this end is going up, and I see 1, 2, 3 x-intercepts, I say n equals 3. This is a third degree polynomial. How many turning points does this third degree polynomial have? Well, take a look. This third degree polynomial has n minus 1 turning points. 3 minus 1 is 2. There they are. Okay, so if we had a 42nd degree polynomial, x to the 42nd power plus minus a whole bunch of stuff, we would say 42 zeros, real or imaginary, and we could say 41 maximum of 41 turning points. Okay? Now, this is a maximum number of turning points, right? And we saw this third degree polynomial. It had 1, 2 turning points for third degree. But what if I have this third degree polynomial? How many turning points does that have? Well, I don't see any maxes or mins here. This has 0 turning points. And that's okay, because I know when I have a third degree polynomial, I'll have 3 minus 1 or 2 as the maximum possible number of turning points. I can have less than that number. I could have 0 turning points. So I don't know that turning points is really particularly helpful for me, but I know that a lot of old school math teachers, i.e. teachers who grew up never having used this in math class, but instead using the slide rule, for them, turning points was a way to help identify their graphs a little bit. Okay? So, what do I want to do with this information? Well, I want to start learning how to graph a polynomial. Okay, and I already have some information about that. For example, I know if I have y equals x to the third, I might have 3 real zeros. I might have 1 real zero and 2 imaginary ones. I also know, because this is a 3, that I could have as much as 2 turning points on the graph. Okay? Let's take this conversation a little further. Let's see what else we can develop. I'd like to consider the following graphs. Y equals x minus 3 to the third, y equals x minus 3 squared, y equals x minus 3. Okay? Think about what they look like. Think in terms of transformations. the x to the third graph has been shifted right 3 places. Or here, the x squared graph has been shifted right 2 places. I'm sorry, 3 places. And here, I see the x to the first line has been shifted right 3 places. Okay? Now, what I argue is that that degree says something about that shape. That degree says something about that shape. Because I know if instead of this, I were to graph y equals x plus 2 to the third, well, that shifts left 2. No, not like that, Mr. Cooper. It's not negative. It looks like that. Notice that same wiggle happening, but now at negative 2. So when I see this factor with a multiplicity of 3, that tells me I've got a wiggle. When I see this factor with this even multiplicity of 2, that means I'm going to bounce on the graph at that point. And if I see this factor raised to the first power, then I'm just going to go straight through that point. Okay? Now, why is this important? Well, if I can get my polynomial into factored form, were I to FOIL this out, x times x times x, I would know that this was x to the third, an odd degree polynomial, positive x times positive x times positive x, with a positive leading coefficient. I would know that this end would go up and this end would go down because I know my end behavior. I also know, thanks to Thomas Harriot, that this has x-intercepts at 1, at 2, and at 3, because I can set each factor equal to 0 to find the zeros or x-intercepts. And so then graphing is simply a matter of connecting the dots and following the end behavior. I always want to start by noting what end behavior I have. Okay, it won't always be third-degree polynomials. In fact, they won't always have a multiplicity of 1. What if I make this a 2? Now it's x times x times x squared. This is going to be an x to the fourth polynomial. Well, what do we know about x to the fourth polynomials? This goes up and this goes up. I still have zeros at at 1, 2, and 3. So let's try and connect the end behaviors through these x-intercepts. Okay? So I'm going down and I'm coming up and I'm going. I'm supposed to be up here. I'm supposed to be up here, not going down here. Well, wait a minute. Maybe I should try going the other direction. Okay? So I'm starting here and going down through there and up through there. But wait, it's an even degree polynomial, and both ends are supposed to go up, and that's not going up. There's something wrong here. And you know what it is? It has to do with this. See this? We call this a multiplicity of 2. This factor has a multiplicity of 2. And whenever we have an even multiplicity, that means the graph bounces off that x-intercept. Okay, so let's see what that looks like. We know that both ends are supposed to go up. We know we're going to pass through 1, through 2, and 3 is an x-intercept. But at 3, I need to bounce. So I pass through at x equals 1, I pass through at x equals 2, and I bounce off the x-axis at 3 because of that. There's my polynomial. Now, graphing polynomials, really, from factored form, the only thing I want is the correct shape with appropriate bounces I want to know where the x-intercepts are, and give me the y-intercept as well. How do we find a y-intercept? Well, we've been talking about this for a while. We put x equal to 0. So I end up with 9 times negative 2 is negative 18 times negative 1 is positive 18. And so there's my graph. And so what I'm going to suggest to you is, if I have the factored form of a polynomial, it's really fast for me to make a graph. But let's talk some more about these factors and these factored forms. Remember, I just had x minus 3 squared. And remember, we looked at this already and said, oh, look, at 3, the graph is bouncing off the x-axis. Because of this, we're bouncing off that x-axis. If I throw in some extra factors in this polynomial, we're still getting a bounce at 3 because of that multiplicity, that even multiplicity. Okay, but what if I changed that to be that? Okay, so now I've got x minus 2 squared. Well, it's still x times x times x squared. It's still x to the 4th. So I know that both ends still go up. Y up and not down. Positive times x squared is always positive. So I have a positive leading coefficient here. And where are my x-intercepts? At 1, at 2, and at 3. Now, at 1, I'm passing through. At 3, I'm passing through. But what am I doing at 2? I'm bouncing. Look, I didn't bounce up like y equals x squared. I bounced down. Now some students say, Mr. Kukla, how am I going to know when I'm bouncing up or bouncing down? And my answer to you is, sadly, I don't know until I get there. Okay? So I've got both ends up. I'm starting at 1. I'm passing through at 1. And then I'm coming up to 2. And I'm saying, well, I'm not quite sure what's going to happen there. But I know, because of that multiplicity of 2, I've got to bounce off that point and pass through at 3. Okay? All right. And if instead of there, I have the even multiplicity there, well, now we still have a 4th degree polynomial, but now my bounce is here at 1. And I'm going to pass through 2 and pass through 3. When I see 1st degree, I just pass through. But if I see x to the 2nd or x to the 4th, that means I'm going to bounce off the x-axis. Now, here, I bounced up. When the multiplicity of 2 was here, I bounced down. And when the multiplicity of 2 was here, I bounced up. I don't actually know whether I'm going to be bouncing up or down when I look at the factored polynomial. It's just when I start graphing it do I figure those things out. So what's going to happen here, do you think? 2, 1, 2. Will you try graphing this polynomial? Hey, and by the way, label the y-intercept on your polynomial as well as the x-intercepts and as well as the correct shape through those points. First ask, what degree? Now I see x squared times x to the 1st times x to the 2nd, and so I'm thinking about x to the 5th. But some students like to say, when we're in factored form, they add up the exponents, and that gets them to 5 as well. That method works great about adding the exponents unless we're given in unfactored form. See, this isn't factored yet. We don't have a bunch of factors. And so if you were to say 3 plus 2 plus 1 and say 6th degree polynomial, yeah, no, you'd be terribly wrong. This is a 3rd degree polynomial. So in this form, the degree is the highest power. But in factored form, we want to add up all the exponents. Okay? So what's this look like? Have you tried it yet? Give it a try and come back. We know this is a 5th degree polynomial, so that's my end behavior. We know that there are zeros at 1, 2, and 3. Now, at 1, I see x to the first, so I know I'm just passing through. But at 2, that multiplicity of 2 means a bounce. I have to bounce off of x equals 2. And then what? Well, when I get to x equals 3, there's another bounce. And so there's my graph. Don't forget to label the y-intercept. How do I find a y-intercept? Set x equal to 0. So I get negative 3 squared, or 9, times negative 1, and negative 2 squared is 4. So that's going to be 0, negative 36. And there's the graph of my polynomial. From factored form, it goes pretty fast. All right, so what will this look like? Y equals x minus 1 squared times x minus 2 times x minus 3 squared. Can you graph this polynomial? Pause the video, give it a try. Okay, so 2, 3, 4, 5, fifth degree, positive x, positive x, positive x. So fifth degree polynomial with a positive leading coefficient has the same behavior. So I know this end's going to go up, 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 and this end's going to go down. 1, 2, 3. So what am I supposed to do at 1? I'm supposed to bounce. But look, I'm coming from below, and I'm bouncing down. At 2, I'm going to pass through, and at 3, I have to bounce again. And so there's my graph. And of course, my y-intercept I can get by plugging 0 in for the x's. So 0 minus 1 is negative 1. Negative 1 squared is 1. 0 minus 2 is negative 2. And 0 minus 3 is negative 3, but negative 3 squared is 9. 9 times negative 2 times 1 makes this point here negative 18. Ta-da! We're all done. Well, except this. What if I have y equals x minus 1, x minus 2, x minus 3, but I have a 3 here? Remember what this looked like? This looked like? It looked like the x to the third shifted right 2 places. See that? That's a wiggle. An odd multiplicity bigger than 1, because 1 just passes through. An odd multiplicity bigger than 1 creates a wiggle. A wiggle. And how do you draw that wiggle? Well, just draw a y equals x to the third at that point. So what if I change this a little? And what if I say 2 here? Okay, now I have 6th degree polynomial. I know both ends go up. 1, 2, 3. So because of this 2, I know I'm supposed to bounce here. And because of this 1, I know I'm supposed to pass through here. And now I have to get from here to here, but what's happening at x equals 2? I see a wiggle. Now, there are 2 types of wiggles. Just like there's 2 types of bounces, bouncing up and bouncing down. There's this type of wiggle. Can I connect this to this and this to this without crossing the x-axis? No. So instead of wiggling through like that, my wiggle has to look like that. So just like a bounce looks like a positive x squared or a negative x squared, a wiggle can look like a positive x to the third or a negative x to the third. And I'm not going to know which one I've got until I get to that point and say, how can I connect this with this? I can't do this because that can't connect to that without crossing there. And I don't have any more x-intercepts, just these 3. I've got them already. So I need to find this other wiggle, like a negative x to the third. Okay? And don't forget the y-intercept, which we get by plugging a 0 in for the x's. Negative 2 to the third is negative 8, times negative 3 is positive 24, times positive 1 is positive 24. And there's my polynomial, okay? So, I would love it if you took that information together and said, and graphed, y equals x minus 1 to the third, x minus 2, and x minus 3 squared. Please graph this polynomial. Use your knowledge of the degree of the polynomial, positive leading coefficient to get the appropriate end behavior. Use the fact that factors can help us find zeros, and think about the multiplicity on each factor and what happens on the graph because of those multiplicities. Okay, welcome back. So I know this is 3, 4, 5, 6th degree polynomial. Both ends go up. How do I know both ends go up? Mr. Google, what would it look like if both ends went down? Well, if I had a negative out here, that would take my 6th degree polynomial and flip it over. But I could also do this. This still has an x-intercept at 2, but now it's negative x times x squared times x to the third. And so I get x to the 6th, but it has a negative in front, okay? So it is certainly possible, and I must look every time to see if I have a positive leading coefficient or a negative one. But here, I have positive x to the third times positive x squared, and that gives me positive x to the 6th. So I know both ends go up. I know I have zeros at 1, 2, and 3 because these factors help me find these zeros. When I set a factor equal to 0, I find x-intercepts. Okay, now what's the shape we have through these points? Well, I see at 1 I'm supposed to wiggle. So, is this the shape? Remember, I'm starting here on the left side of 1. How am I going to get to that without crossing the x-axis? And the answer is I can't. So that's not my wiggle. My wiggle must look like the negative x to the third. Okay? So at that point, I'm drawing a negative x to the third or a positive x to the third, and we determined that we wanted the negative x to the third. Now here at x equals 2, because I have a multiplicity of 1, I'm just going to pass through. And then when I get to x equals 3, what does that tell me? That's right, I have to bounce. So there's my graph of the polynomial. Can you tell me where the y-intercept is as well? 0 minus 1 is negative 1. Negative 1 times negative 1 times negative 1 is negative 1. Times 0 minus 2 is negative 2. Times 0 minus 3 is negative 3, but negative 3 squared is positive 9. We have negative times positive, and that gives me 0, 18 here. So when you graph your polynomials, I just need the zeros, the appropriate end behavior. I'm going to be looking to see if we pass through, if we bounce, and if we wiggle. And then I want to see the appropriate end behavior. All of that is pretty straightforward if I'm given or have factored form. Okay? So try this one. Y equals x minus 1 squared, x plus 2, x, minus 2, just to be consistent, and minus 3 to the third. Graph this polynomial. Okay, welcome back. 2 plus 1 plus 3 is x to the 6th, so both ends go up. I have zeros at 1, 2, and 3. But what am I supposed to be doing at 1? I'm bouncing. So I'm going to come down and bounce. At 2, because of the multiplicity of 1, I'm just going to pass through. But what happens when I get to 3? I see a wiggle. Now, is it the negative x to the third wiggle? No, because I can't connect those without crossing the x-axis again. It has to be the positive x to the third wiggle. Okay? And don't forget the y-intercept. So I'm going to have 1 times -2 times -27. So that's 0.54. Okie doke. Okie doke. How about one last one? Okay. Y equals x minus 1 squared, x minus 2 to the third, x minus 3 squared, and let's put a negative in front. All right, pause the video and graph this polynomial. Welcome back. 2, 3, 2. 7th degree polynomial with a negative leading coefficient. Remember, when we have an odd degree polynomial with a negative leading coefficient, that side is up and that side is down. Okay, so I have intercepts at 1, 2, and 3. We're up over here and down over here. Now, what am I supposed to be doing at x equals 1? I'm supposed to be bouncing. Bouncing. What am I supposed to be doing at x equals 2? Well, at x equals 2, I'm either going to wiggle like a positive x to the third, but I can't connect that with that, or I'm going to be wiggling like a negative x to the third, and I can connect those. So my graph is going to wiggle here, and then what are we going to do when we get to x equals 3? I see an even multiplicity, and that means a bounce. I'm going to bounce off the x-axis. Here I bounced up, here I bounced down. When I look at these, all I know is I'm going to bounce. Don't know whether it's up or down until I get to that place in the graph. And that place in the graph tells me whether I'm going to bounce up or bounce down. Let's talk about this bounce at 3. So I just came out of wiggling from 2 and my function is down here in negative land. I see that a bounce happens at 3. Can it be this bounce? How could I connect these two? The answer is I can't. So it's not going to bounce up, but instead I have to bounce down. All right? And of course, don't forget the y-intercept. I plug in a 0, I plug in a 0, I plug in a 0, and don't forget that negative. So negative 1 times 1 times negative 8 times positive 9. So 72, positive 72. 0, 72. And there's our graph. So we graphed by appealing to the degree of the factors known as the multiplicity, but also the degree of the polynomial, the overall degree of the polynomial. Here we had a 7th degree polynomial with a negative leading coefficient, and that gave us the end behavior. I always want to look at and determine the end behavior even before I put my x-intercepts down. I want to be thinking about the end behavior of the polynomial, and then pass through those x-intercepts or bounce off those x-intercepts. Okay, it's still an x-intercept there, but it doesn't go from positive to negative at x equals 1. We're going positive, 0, positive. All right. Well, so there's our first chat about graphing polynomials. You know, you will see some other polynomials, like this one. Y equals 3x to the third minus 15x squared plus 18x. And now I sort of say, well, I don't know how to graph that. I mean, I know it's a third degree polynomial with a positive leading coefficient, so I know it's end behavior, but I don't know, I can't find any of the x-intercepts. And that's because I'm not looking in factored form. So the first thing I want to try is factor. And I notice I can take not only a 3 out of each of these, but also an x. Y equals 3x, and I'm going to have x squared minus 5x plus 6. Hey, and that's trinomial factors. X minus 2, x minus 3. And so now when I set each factor equal to 0, I get x equals 0. I get x equals 2. And I get x equals 3. What about the multiplicity? Well, all of them have a multiplicity of 1. So I'm just going to be passing through with this third degree polynomial with a positive leading coefficient. Passing through 0, passing through 2, passing through 3. And there's my graph. Now, what I don't know from these really quick polynomial graphs is how high is that maximum? Or how low is that maximum? And so I really don't care which of these red, green, blue graphs you do. All three of them have the appropriate end behavior and the appropriate behavior at each of these zeros. They all just pass through. But it may be the case that you run into some problems where you have to do some factoring first. Sometimes we're given factors, but other times, like y equals x to the third minus 3x squared, if I have a situation like this, the first thing I want to do is factor. I can take out an x squared, I have x minus 3. This x squared, you could think about it this way. So, third degree polynomial with a positive leading coefficient. I know that this end goes up and this end goes down. But what do you see? Well, at x equals 0, I see a bounce. Boing. At x equals 0. And at x equals 3, because there's a 1 there, well, I'm just going to pass through at 3. And there's my graph. Okay? So, from factored form, pretty easy. If it's not given to me in factored form, why don't we write it in factored form? Okay? That's a doable thing for us as well. All right, how about this one last one? Y equals x to the fourth, x to the fourth minus 8x squared plus 16. Well, fourth degree polynomial, positive leading coefficient, both sides go up. If I plug a 0 in for x, 16 is the y-intercept, but that's not a lot of stuff to know, is it, right? I know this is up, and this is up, and I'm passing through 0, 16. But what about x-intercepts? Am I bouncing? Am I wiggling? Am I passing straight through? Does it have any real x-intercepts? And I'm not going to know stuff like that unless I factor. And that's why in the Algebra Basics unit, we practiced factoring things that look like this. So there's my factor. Oh, but wait. Aren't these both difference of squares? X minus 2, x plus 2, x minus 2, x plus 2. And notice how I have 2 of those and 2 of those? Well, then this can be rewritten as x minus 2 squared and x plus 2 squared. So I see my fourth degree polynomial with a positive leading coefficient, but now in factored form I see some x-intercepts at 2 and negative 2, and I'm bouncing at each of those places. So what's my graph going to look like? Well, negative 2, positive 2, this end is up, this end is up. And what am I supposed to do at negative 2? I'm supposed to bounce. And what am I supposed to do at positive 2? I'm supposed to bounce. And there's my graph. So, to summarize, 1, I need you to think about multiplicity and to think about end behavior. Remember, a positive leading coefficient, with an even degree, both ends go up. And a negative leading coefficient for an even degree polynomial, well, both ends go down. For an odd degree polynomial, with a positive leading coefficient, we go up as x heads to 0, infinity, and down as x heads to negative infinity. But if I have an odd degree polynomial with a negative leading coefficient, then this side is up and this side is down. All right, well, I hope that this was helpful for you, and I look forward to exploring multiplicity more in our next video. All right, where I think the plan is that we go backwards. Can't wait. See you there.